Welcome to today's deep dive. If you're joining us, you are probably someone who wants to cut through the massive amount of noise surrounding AI right now.
Right, there is a lot of noise.
There really is. And if that's you, well, you're in the exact right place. Because today, our mission is to explore a truly fascinating new research paper out of Stanford and UC Berkeley.
Yeah, the LLM-as-a-Verifier paper.
Exactly. I mean, everyone in the tech world is just completely obsessed with how well AI generates answers, right?
Right.
We hear nonstop about scaling laws for making models write better essays or, code faster.
Oh, constantly.
But today we're focusing on a critical and honestly severely underexplored frontier, which is how AI actually grades or verifies those answers.
Yeah, and to help visualize the sheer scale of this, I mean, imagine the space behind me just shifting into a massive futuristic grading hall.
Okay, I'm picturing it.
Like towering, sky-high stacks of highly complex technical exams. And in the center, there's just a single overwhelmed judge trying to stamp every single page. That is the scale of AI verification we're dealing with today.
And usually, when we think about taking a test, there's this expectation of absolute finality, like a high school math exam.
Right.
You hand in your paper, the teacher breaks out the red pen, and you either get an A or an F. It's a very clean binary system.
We gravitate toward that because it's comfortable. Human beings, we really like to categorize success and failure into neat little boxes.
Oh, absolutely.
But that binary mindset is exactly what's holding back the entire field of artificial intelligence right now.
Because before we can understand the new solution these researchers came up with, we really have to understand why the current system, having an AI act as a judge, is fundamentally broken.
Right, and the core problem there lies in what we call discrete scoring.
Okay.
Today, if you want an AI to evaluate another AI's work, you typically just prompt a standard language model to act as a judge and give a discrete score. You literally just type, rate this trajectory from 1 to 5.
Which, sounds totally logical on the surface, right? We rate Uber drivers and restaurants from 1 to 5 all the time.
It does sound logical, but what's fascinating here is what happens under the hood of the language model. The model actually has this whole internal distribution of mathematical weights.
Right.
It's a rich landscape of probabilities across all the different possible scores. In machine learning, we call these the logits.
The logits, right?
Yeah, so the model might internally compute, well, based on the data, I am 49% sure this is a 4 and 51% sure this is a 5.
Oh, I see.
But because your prompt forced it to output a single integer, it collapses that entire rich, nuanced distribution of thought into a single coarse number, a 5.
It just completely throws away all its mathematical uncertainty.
Exactly.
Okay, let's unpack this. It's like asking a world-class sommelier to taste two complex, drastically different wines, but forcing them to only rate them as good or bad.
That's a perfect analogy.
Right. You lose all the nuance. And they both just get labeled good. And the consequences of throwing away that nuance have to be pretty severe.
They are. I mean, the researchers point out a shocking statistic here. On a really complex coding benchmark called Terminal Bench, this course scoring results in a 27% tie rate between completely distinct trajectories.
You need 27%.
Yeah.
So more than a quarter of the time, the AI judge looks at two entirely different ways of solving a coding problem and just shrugs.
It gives them the exact same score. Because it's forced into that 1 to 5 box, it doesn't have the vocabulary to say, this one is a 4.1 and this one is a 4.8.
It just stamps them both a 4.
Exactly.
Which means you can't rank them. You can't figure out which AI is actually getting smarter.
Right. Which means the whole process of improving the models just grinds to a halt. And previously, the only way to fix this was training these highly expensive custom reward models.
Which failed to generalize across different domains, right?
Yeah.
Like a coding grader is useless for a medical task.
Exactly. Which sets the stage for the paper's training-free solution.
Yes, and this is where it gets so cool. Because forcing a discrete choice strips away the AI's nuance. The researchers found a way to let the AI express its uncertainty continuously.
Right. They scaled verification.
And the first axis they used for this was granularity. Instead of a single digit, it computes the expectation over the distribution of scoring token logits. But to get a 1 to 20 scale, they ran into a clever little hack.
This is such a brilliant, specific detail from the paper, because if you want to expand to a 20-point scale, language models don't read the number 20 as one thing.
Right, tokenization.
Exactly. Depending on the model, a 20 might be split into a 2 token and a 0 token.
Which totally breaks the probability math.
It ruins it.
Yeah.
So to get these log probs accurately, they used a letter-based scale instead of numbers.
The A through T scale.
Yes, they literally just swapped out 1 to 20 for A to T. Those letters are always single tokens, so it forms a clean mathematical highway to pull the exact probability.
That is just so brilliantly simple. And we can see exactly why this level of granularity matters in this case study they did on a task called Query Optimize.
Right, from Terminal Bench V2.
Yeah, so an AI was asked to optimize a super slow database query. And one AI took a really robust approach. It waited 5 full minutes and tested its work on the actual live database.
Very thorough.
But the other one, the failing AI, it just got lazy. It created a brand new empty database on the side and completely bypassed the test.
And if you use a standard discrete 1 to 5 judge on those two...
It tied them 88 out of 100 times.
Yeah.
It couldn't tell the difference.
Yeah.
But by scaling that granularity up to 20 tokens using the A to T scale and using continuous probability, the tie rate dropped to 0.
Absolute 0, because deep down in the logits, the AI harbored slight mathematical doubts about that empty database trick. So the continuous verifier chose the correct one 77 out of 100 times.
Just incredible.
Yeah.
But granularity is only the first axis. What about the other two?
So the second axis is repetition. Even a fine-grained score has variance, right? So they just repeated the evaluation process, say, k equals 16 times.
To average out the random noise.
Exactly. And the third axis is decomposition. Instead of asking one massive monolithic question like, is this good? They broke the criteria down into specific parts.
Like, does it meet the specification? What is the output? And are there any errors?
Yes, because monolithic prompts introduce bias. You have to force the verifier to evaluate the work from multiple independent angles.
Okay, here's where it gets really interesting, though, and I have to push back a little.
Sure.
Wait, if you increase granularity to 20, and then you run it 16 times, and you decompose every prompt, doesn't it take way more compute? Are we just throwing processing power at the wall?
I mean, that is the immediate concern. But the real magic is how these three axes work together.
Okay.
Granularity sharpens the signal within a single pass without really adding cost. Then repetition averages out the noise. Together, they don't just add cost, they form a highly calibrated score.
I see. But still, if we are doing all these repeated, highly granular evaluations to get the perfect score, comparing every single generated answer against every other answer would take massive amounts of computing power, right?
Yes, it would. And that introduces a classic math problem. If you run a round-robin tournament comparing n candidates, it takes big O of n squared pairwise verification.
The O of n squared.
Right. So if you have 20 candidate answers, that is a ton of very expensive AI queries.
So how do we make this practical?
The researchers introduce what they call the probabilistic pivot tournament, or PPT. And step 1 is something called a random Hamiltonian cycle.
Also known as a ring pass.
Exactly, a ring pass.
Okay, so instead of everyone playing everyone, we basically put all the candidates in a big circle.
Right.
Each candidate passes their answer to the left and to the right, which means every candidate is evaluated once in the A position and once in the B position.
Yes, which is critical because language models have terrible positional bias. They often just prefer whatever you show them first.
So it's like making sure every debate team gets to argue first once and second once, so there's no first mover advantage.
That perfectly cancels out the bias.
That makes total sense.
And then comes the pivot selection. Based on that initial ring pass, they just take the top candidates, the absolute best ones.
The pivots.
Right. And then they only spend the remaining compute budget comparing candidates against those top-tier pivots.
Wow, so you aren't wasting compute comparing terrible answers to other terrible answers.
Exactly. It cuts the cost down drastically from n squared to big O of nk squared. You concentrate your budget only on the most uncertain top-tier candidates.
And the results of this are just wild. Using this method, entirely zero shot, meaning no extra training at all, they hit 86.5% on Terminal Bench V2.
Which is state-of-the-art.
Yeah. And 78.2% on DesTW Bench Verified, and 73.3% on Medgen Bench.
It shattered records across coding, robotics, medical AI tasks. It's a massive leap.
It really is. But, we've established that this verifier is the ultimate judge at the end of a task. The researchers discovered a surprising side effect, though, didn't they?
They did. They found out this continuous scoring is also highly effective during a task.
Right.
They introduced this concept called value order correlation, or VOC. Because the score is so fine-grained, it actually correlates strongly with chronological task progress.
Okay, so picture this. You ask an AI to install PyTorch, which was the example from the source. On a successful run, the score smoothly goes up as the AI reads the file, installs a compiler, and installs Torch.
Like a progress bar.
Exactly. But on a failed run, where the AI gets confused and accidentally installs this massive Torch Vision package and runs out of disk space.
The verifier score just stays flat or drops the moment it makes the mistake.
So what does this all mean for you listening? It means you won't have to wait 30 minutes for an AI agent to finish a job, only to find out it failed at step 2.
Right. The researchers even built extensions for Claude Code and Codex. They call it Turbo Agent.
Turbo agent, yeah.
It acts as a real-time progress bar. So you can pause or roll back an AI before it ruins your files.
Which is incredibly practical.
And if we connect this to the bigger picture, it solves a huge issue in reinforcement learning, or RL, called the credit assignment problem.
Okay, explain that one.
Say you have a robotic arm trying to pick up an apple. It makes 100 tiny movements. If it drops the apple at the end, a standard binary judge just says, you failed.
So the AI has no idea which of the 100 movements was the bad one.
Exactly. It's a sparse reward.
Yeah.
But by acting as a dense step-by-step reward, this new verifier tells the robot, hey, your score was going up until movement 42, and then it tanked.
It teaches the models not just that they failed, but exactly where they went wrong.
Right. And it improves sample efficiency by 1.8 times on the Libero robotics tasks using DSRLSC,
Wow.
and 1.1 times on math tasks using GRPO.
That is just phenomenal. Okay, we've covered a lot of ground today.
We really have.
Let's summarize for everyone. By moving from discrete, coarse AI judges to continuous probabilistic verifiers.
Which we scaled via granularity, repetition, and decomposition.
Exactly. By doing that, we can dramatically improve how AI agents select the best answers, write code, and even move robotic arms.
And we can do it efficiently using the probabilistic pivot tournament.
Yes. It's a total paradigm shift.
It really is. And, this raises an important question.
Wait, I love these. Lay it on us.
Well, it's something not explicitly resolved in the discussion, but if an AI can now accurately evaluate its own step-by-step progress in real time with continuous scoring,
Yeah.
what happens when we close the loop entirely?
Oh, wow.
Right. Could future AI agents proactively redesign their own foundational criteria mid-task? Like if they notice their verifier score plateauing, could they effectively rewrite their own grading rubric on the fly as they encounter novel problems?
And the AI rewriting its own test while it's taking it. That's intense.
It completely changes the trajectory of autonomous agents.
It really does. Well, that is a wild thought to leave off on. Thank you so much for joining us on this deep dive. Keep questioning how the information you receive is generated, and more importantly, how it's verified. We'll see you next time.